Okay, it's been a little while since I created the video here, so let me just explain what we've been working on. So here's our battery. I'm working on the power system. This is a 3-cell battery. This 3 cells are hooked up in parallel, so it gives us the cell voltage of 3.7 volts at about 6,000 milliamp hours. So kind of two different problems here with the power system. Obviously, the power system is very important, and we've had trouble with it in the past. So it's really important that we make a really robust power system that's capable of working under different conditions, and possibly with things breaking, components failing, we still want the power system to work. If we don't have a power system, obviously we have nothing else, and all the circuitry is kind of trivial at that point. So this is our original setup here. What we do is we have the solar cells, which run the charger. The charger supplies current. It can supply current directly to the system, or it can supply current to the battery, or both. So this works fairly well. The issue is that the charger can only supply a maximum amount of current. So the max current coming out of the charger is something like 600 milliamps. 600 milliamps, it's going to charge the battery, it's going to drive the system, but the power, that current has to be shared amongst these two loads. So we have plenty of power in our PV cells here, in the solar cells. So we don't want to limit ourselves with a charger with running the system and charging the battery. In the right lighting conditions, we can get far more power than that out of the cells. So we want to efficiently use that power and not kind of just waste it because our charger can't provide enough current to both of these. So the solution to that is to use Schottky diodes to limit the current direction, the flow of current between different sources to the regulator. So this goes to the system. This is the 3.3 volt regulator into the system. So here the difference is that our solar cells actually drive the system directly through a diode, okay? Or it simultaneously will drive the charger, which will charge the battery, and simultaneously the battery can drive the system directly through a diode. Okay, so and in addition, you can get, you will get inherent current flow between the solar cells through the charger to the battery and then through to the system. So this is going to happen, but if there's power from the solar cells, it will most likely flow directly anyway. So there's a couple different paths that the current can take here, and this is good because it allows things to fail and the system to continue working. If the battery fails, we know we can get power during the day with the solar cells. If the solar cells fail, we know we'll get power directly from the battery, at least for a while. If the charger fails, we know we'll get it from the battery until the battery runs out, and then from the cells. So a couple different options here, and those options are always good. And the probably largest selling point of this configuration is that there's almost no circuitry here. We have 2 Schottky diodes. They're chosen for their low voltage drop, so we don't lose a lot of voltage passing through these. And they are less likely to fail because they're only one component. So this is extremely important for us, the simplicity of this. So this design is really something that we're excited to try. So that covers the somewhat simple problem. The next problem has to do with the discharge of the battery. So again, this is our battery. 3 cells, and about 3.7 volts. You'll see here, this is the typical discharge. The x-axis is time. The battery starts up here, maybe around 4 or 4.2 volts. As it discharges, it's obviously not linear. It's going to discharge through this 3.8 range. When it gets to 3.3, you can see I labeled this off. We want the battery to shut off here. We don't want any more current to flow out when it gets to this point. And so this is our primary problem. When the battery and the solar panels are cycling through day and night conditions and charging and discharging, we never want the battery to go down below this point. So you can see a couple of the different points I have here on a little chart. The battery will self-protect itself at 2.7. So the battery will say to the load, you know what, I'm way too discharged, I'm not actually going to discharge any more current at this point. At this point though, the problem is, there's two problems. One, the battery has already done a small amount of damage to itself, possibly. And two, this range here, between 2.7 and 3, the charger goes into what we call preconditioned mode. So the battery needs to be preconditioned between what would be 2.7 and about 3 volts, or anything below 3 volts really. So 3 volts maybe be about here. This point, or this range, the charger will sense that battery voltage and will go into preconditioned mode. So the reason that preconditioned mode exists is basically so that the battery doesn't explode. So we don't want the battery exploding, and neither do most end users. So the idea here is that the charger limits the current that it's putting into the battery, because the lithium polymer batteries can explode if they're in this range below 3 volts here. They're in this range and they get a full charge current. That current surge can actually cause the battery to explode. So we want to stop the discharge at about 3.3 volts. That way we're well away from the preconditioned current. So the preconditioned charge mode, the only difference with it is that it only charges at about 10% its normal rate. So effectively, it will prevent it from exploding, but it will also charge very slowly through this range, very slowly. And we don't want to wait for that. So we rather just not go into this range. We have the solar panels to recharge everything. We might as well just say, you know what, shut off here just to be safe, charge back up, and then come back on a little later. So that being said, it's very important to shut off the battery at this 3.3 volt level. And again, we can't rely on the battery's own circuitry of 2.7 volts because it will be too low and will already be in that preconditioned state. You can see in the battery here there's a little circuit board in there. That's actually the internal circuitry in the battery. So this is a high quality battery from SparkPhone. If you get batteries directly from other manufacturers, particularly some of the cheaper ones from places like Deal Extreme, those batteries are great and they're fine, but they don't have protection circuitry in them, so they will discharge all the way, and then you hook them up to a charger that's also not very high quality, and the battery can definitely explode. This right here is the discharge graph. This is our optimal case. Battery's discharging, it gets to here and it shuts off. The voltage drops completely, the system shuts off. So we built this system here with a comparator and a reference voltage. So the battery voltage comes in. This input to the comparator here is 0.7 volts. This input is tunable through this resistor voltage divider. And so you've got two inputs. And so all the comparator does, for those of you who are not familiar with this, is it just compares these two voltages and gives you an output. So if this voltage is higher than this one, it outputs high. If this one's lower than this one, or if this one's lower than this one, it outputs low. So it will switch states. It has a really high gain, so that the output will switch very quickly, so that we kind of get this sort of thing. So here our reference voltage goes lower and it will shut off. So you can hook them up as inverting or non-inverting. So if I flip these two wires around, the on-offs will just be the other way around. So when the voltage goes low, it turns on. When it goes high, it turns off. The output of this drives a transistor, and the transistor controls power to the system. So you can actually see the built version of this circuit here. So we have our voltage, reference voltage here. This is our transistor. This is our comparator, special low voltage comparator. This is our tuning resistor. This is a this is another resistor to kind of change the exact tuning. This one changes the reference voltage. This one changes the other voltage that we're comparing, and this is changes the hysteresis feedback voltage, which we won't get into, at least in this video. So you can see it's a lot of fun soldering this together. Unfortunately, we put this circuit together. I built this and we will not use it. Two problems. One, it's actually kind of hard to get this transistor to fully switch states because of the low voltages we're dealing with here. Two, this voltage regulator and the comparator actually draw a decent amount of current even when the system's off. So you have to remember that this is always in line with the battery. Even when this is off, you know, we're still looking at the voltage, comparing it, because we need to evaluate it to turn it back on. So, you know, we get into this chicken or the egg problem time and time again, where it's your circuit that senses whether to turn the system on, your power regulation circuit, actually consumes power itself. So what do you power that off of? So, you know, it's kind of a circular problem. You know, you can say, oh, well, I'll have another battery. If you have another battery, you know, okay, now that one needs to be charged and it needs its own regulation circuitry. So that problem comes up a lot. So the solution, ultimate solution to this, you might be wondering what that is if we're not using our comparator circuit. The ultimate solution is to use a voltage regulator. So this system here will actually, I'll use the other diagram. So you can see here we have the system is actually down here. There's a regulator first. This regulator actually incorporated, we were able to source a regulator that actually has an enable pin. And the important thing is the enable pin is enable high. So when the voltage goes high on the enable pin, this turns on. So that way we can just feed this power into the system through a voltage divider, and then have it go directly into the enable pin. And we check the input on the enable pin and versus the output. And the nice thing is, on this particular regulator, when the enable pin goes on, you get a very, very clean drop in voltage when it goes off or when it goes on. Your voltage is very, very sudden. You know, it turns on instantaneously. Not something like this where, you know, it slowly turns off depending on what your enable voltage is. So it's very good about being a very steep drop off and instantaneous power shut off. In addition, it also seems to have some hysteresis voltage built into it to prevent it from triggering back and forth quite a bit. So that's what we're going to be doing with the power system. We haven't actually gotten the new regulator yet, so we're planning to get that in a week or so. So we'll hook that up and see how it works. But that's the overall review of what we've been doing with the power system here in the last few weeks of development.